As wireless mobile devices become more and more capable, the demands for longer battery life continue to increase. Optimizing the operation and efficiency of the individual components in a mobile device is key to improving its overall efficiency. This video will focus on design verification testing of onboard DC to DC converters in mobile devices. The circuit component shown here provides several different internal voltage levels from the single voltage level provided by the battery. They are often incorporated into a single package known as a power management unit or power management integrated circuit. DC to DC converter efficiency is a key parameter to optimize in the design of these components. The efficiency of the DC to DC converter and all the components used in the design directly affect the operating life of the battery-powered device. Efficiency must be measured over the entire range of current required by the device in use and over the battery voltage range from full charge to low charge. Because different circuits of the wireless device often switch between various sleep modes and active modes, the turn-on time and rise time of the DC to DC converters are also key design parameters that affect efficiency. Minimizing the transition time reduces battery drain when no productive activity is occurring in the device. Measuring and controlling these turn-on times and rise times is a key part of improving device efficiency and battery-powered operating time. First, let's look at efficiency measurements. A typical test configuration using conventional test equipment would require a power supply, an electronic load, 2 external current shunts, and a 4-channel data logger for the measurements. In addition, the efficiency of the converter must be calculated from the raw voltage and current measurements on the input and output of the DC to DC converter. These measurements must be correlated in time if you're testing the converter under dynamic conditions. Thorough testing for efficiency requires setting the power supply to voltages representing the battery voltage at full charge, nominal level, and the drop-out or turn-off level. For each voltage input level to the converter, the load on the converter's output must be stepped or swept over the load current range that is expected in actual device operation. This may range from microamps in sleep mode to hundreds of milliamps in transmit mode. Setting up the source and load manually and making all these measurements with conventional test equipment can be extremely time-consuming. As the load current is stepped or swept, a corresponding measurement of the input voltage, input current, and output voltage must be captured and logged for analysis. Accurately measuring these widely varying current levels will require changing the shunt values to minimize the voltage drop across the shunt. This makes it difficult to automate the test process, and therefore the design verification task is more time-consuming. There is a better test solution from Agilent Technologies for making these challenging measurements faster and with more accuracy. The Agilent N6782A source measure unit installed in an N6705B DC power analyzer mainframe has specialized features for testing DC to DC converters used in PMUs. This is a modular system where up to 4 SMUs can be installed in the mainframe for maximum flexibility. Each SMU can be configured as a source or load and includes voltage and current measurement capability. Diagrammed here is the setup for testing a single DC to DC converter. When configured as a source, the N6782A SMU provides programmable voltages with faster settling and less ringing under dynamic loads than a general-purpose power supply. When configured as a load, the N6782A SMU has unique attributes well suited for testing DC to DC converters. With 2-quadrant operation, it can perform as a constant voltage or constant current electronic load. The built-in arbitrary waveform generator makes it easy to create a wide variety of dynamic loading profiles to apply to the converter. This example shows the SMU's load current changing from 500 microamps to 1 amp during a load sweep and then returning to its minimum value. The N6782A SMU has an internal high-speed 200 kHz digitizer with seamless measurement ranging so you can accurately capture the entire dynamic range of measurements in a single pass. This capability means that you can capture and view the dynamic voltage and current consumption of the device under test with an effective resolution of up to 28 bits. The internal ammeter eliminates the need for external shunts. When combined with the Agilent 14585A software, this solution has the ability to automate your test process and greatly reduce the time spent in design verification of DC to DC converters. Using the built-in ARB, you can create waveforms up to 100 kHz to simulate dynamic loads on a device under test. This screen shows the process for setting up a swept load waveform. Here is an example of the results of an efficiency test on a DC to DC converter. The load was swept from 500 microamps to 1 amp, while the input and output voltage and current were measured with the digitizers. Using a formula created in the 14585A software, the efficiency, shown in the pink trace, is displayed as a percentage directly on the screen. The results range from 80% at full load to about 93% at the maximum efficiency point. To watch a video of this test in action, go to Agilent Tube and look for DC to DC converter efficiency measurement. Moving on to an example of turn-on time and rise time testing, here you see the results of an actual turn-on test. Marker number 1 is placed at the beginning, and marker number 2 is placed at the point where the output voltage is at 90%. The time difference between the markers is 1.5 milliseconds. Clearly, the high-speed digitizer in the N6782A is essential for this test. To watch a video of this test in action, go to Agilent Tube and look for Testing a DC to DC Converter. As you have seen here, thorough testing of this key component used in mobile devices involves capability beyond that of conventional test equipment. The Agilent N6705B with two N6782A SMUs uniquely provides the flexible source, dynamic load, and high-speed measurements you need for accurate design verification of DC to DC converters. In addition, the 14585A control and analysis software automates this operation and dramatically improves your design effort efficiency. For more information, visit the Agilent website at www.agilent.com/find/N6782.